Hello and welcome. This is SFU Math 232. My name is Brenna Davison. This is section 4.4, a first look at eigenvalues and eigenvectors. This is an enormously popular, well, I don't know if it's popular, but it's definitely an enormously important topic in linear algebra. Okay, so let's take a run at this for the first time. And what we're going to start with here is the fixed point. We saw this earlier. We defined, we used the word here, fixed point. So if there was a vector x such that when you operated on it by a, like you multiplied a times x, you got back x. That is called a fixed point of a. And it's easy to see with this equation here, if x is 0, then a times 0 will be 0. So the vector x equals 0 is a fixed point, and that's called the trivial fixed point. It's not very interesting. Okay, if we have the equation ax equals x, we want to determine the fixed points. We can rewrite this in this way. So here's what I think we also saw this earlier, but we're here. Let's get the pen oriented properly here. Ax equals x, and then what we can do is put 0 equals x minus ax, and then we can factor that this way. Okay, and the 0 is still here, so that yields this thing right here. Okay. So that was our fixed point seen before, and now what we're going to do, well, actually, let's get this theorem first, and then we're gonna change this. We're going to change this a little bit, but first let's get this theorem. If we've got an n by n matrix, then the following statements are equivalent. A has a non-trivial fixed point. I minus a is not invertible, that is, it's singular, and that singular would be then tell you that the determinant of I minus a is 0. So where does this theorem come from? This is just coming directly from our unifying theorem that we've been keeping adding to, and we'll add to again today. So let me just remind you of this. We have our unifying theorem that keeps getting more and more parts as we go along, and that is in its latest incarnation that we've seen is in 4.2.7, and I'm just going to write what it says there. Ax equals 0 has only the trivial solution, and then that is equivalent to saying a is invertible, and that is equivalent to saying that the determinant of a is not 0. Okay, but that's part of our unifying theorem. So if you take a look here, all these three things is a negation of those things. So we negate those things. Ax equals 0 has a non-trivial solution. A is not invertible, and the determinant is 0. So we negate those three things, and then we negate, and then we apply that theorem to the matrix I minus a, and then you'll get this here, theorem 4.4.1. It's actually really, in some sense, nothing new. It's just an application of what we've already seen before. Okay, so that is the fixed point scenario. Now what we're going to do is take a look at a similar equation, but we are going to allow for a scalar, which we will always call lambda. And we are looking, you can see this equation here, ax equals lambda x. In the fixed point world, lambda was equal to 1. But now we are going to consider any possible values of lambda as scalar, a real number. Okay, lambda is an eigenvalue of a if there's a non-zero vector x such that this equation holds true. I mean, if x is 0, then it doesn't matter what value of what the value of lambda is; it will always be true. Okay, so we look for the values of lambda such that we can make this statement here true for some non-zero values of x. Okay, and if we find one of those values of lambda, we call that an eigenvalue. And then all the vectors that make this statement true for that value of lambda are called the eigenvectors of A corresponding to that particular eigenvalue lambda. Okay, so this is a big if here. Only certain values of specific values of lambda will work. Okay, so every matrix has some specific values of lambda that will work. It's not an arbitrary constant. Okay, so let me just make clear note of that. Only specific values of lambda will work. Okay, so just like we had the previous theorem on the last slide, if we've got a n by n matrix and we've got a scalar lambda, then the following statements are equivalent. Lambda is an eigenvalue of A. The linear system lambda I minus A x equals 0 has a non-trivial solution, and the determinant of this matrix, lambda I minus A, is 0. This is exactly the same statement as the previous theorem, except instead of lambda being equal to 1, it can be an arbitrary scalar. Okay, so I'm just going to just say a couple of things here. Notice if we have, notice that if this is an if too, this won't be true for all matrices A, but say we have a matrix A that has an eigenvalue like this, where lambda for say is equal to 2. We would then say, that lambda equals 2 is an eigenvalue of the specific matrix A. So let's just say then, so lambda equals 2, so that means lambda equals 2 is an eigenvalue of A. Okay, if that's the case, and we then find vectors x such that ax is 2x. So we're going to find these vectors now. Ax equals 2x. Then what happens when A acts upon x? It produces the result 2x. That is a scaling operation. So there's no rotating of x or anything like that. It simply gets, in this case, 2 times longer. So that's what I want to just point out. Okay, so when A operates on these x, the ones that are the eigenvectors, the result is scaling only. Okay, in this case, the vector is made. The vector x is stretched by a factor of 2, the value of the eigenvalue. I don't want to write that. I want to write factor of 2. Okay, there's no rotation. When A operates on an arbitrary vector, we can have scaling or rotation. Okay, so we're going to have some definitions again. Since most lectures we have that. So we can talk about this stuff. We call this determinant lambda I minus A equals 0, the characteristic equation. And when we associate that, when we just take the polynomial that's generated here and say that that's P of lambda, then we call that the characteristic polynomial of A. We're going to see how this works through a whole bunch of examples. Okay, so here we're on our first mission to find eigenvalues, and we've got a matrix A, and we're going to attempt to find the eigenvalues of A. Okay, so let's just recall what the theorem tells us. One, it tells us that lambda is an eigenvalue of A is equivalent to saying that the determinant of lambda I minus A equals to 0. Okay, so we use this to find the eigenvalues. Okay. Okay, so let us, this is going to have to be, well, it should be even by the end of this lecture. We're going to do so many examples like this. What you want is to get that out of your head whenever you need it to find an eigenvalue. Okay, so let us just do that. I'll do it sort of in gory detail the first couple of times, and then I'll sort of shorten the procedure as I can do things in my head. So I'm going to take the determinant of lambda times I minus A. That is a matrix, minus the matrix A. And I'm going to set that equal to 0. Okay. Clearly, I mean, in this case, this thing here is 2 by 2, so I picked the 2 by 2 identity matrix. If I was doing a 3 by 3 matrix, I would pick the 3 by 3 identity matrix. The dimensions of I and A must match. Okay, so let's proceed with this. I multiply the scalar lambda times I get this, and then I'm still going to subtract A. And I'm going to, after that, take the determinant, and then I'm going to set that equal to 0. Okay, keeping going here. That means I'm going to be taking the determinant. Okay, lambda minus 0 is lambda. 0 minus 6 is minus 6. 0 minus minus 1 is 1. And lambda minus 5 is the last entry here. So this is subtracting two matrices. And then I'm going to take the determinant. So that is AD minus BC. That is going to be this thing here. Lambda times lambda minus 5 plus 6. And I'm going to set that equal to 0. Okay, so I'm going to have to simplify this, expand and then simplify and then see what the roots are. This is going to be minus 5 lambda plus 6, and then I can see, oh, that's lambda minus 3 times lambda. I'm factoring that, lambda minus 2, and that is going to be equal to 0. So I have now found the two eigenvalues. They are lambda 1 is equal to 2 and lambda 2 is equal to 3. Okay, these are the two eigenvalues. Okay, just for some nomenclature, P of lambda equals lambda squared minus 5 lambda plus 6 is called the characteristic polynomial. Okay, so each matrix has a characteristic polynomial. And when we write this, lambda squared minus 5 lambda plus 6 equals 0, that is called the characteristic equation. Okay, next point. Each eigenvalue has an eigenvector or eigenvectors. Okay, so let's make a note of that. Each eigenvalue has associated eigenvectors. Okay, so how do we go about finding those? What we do is we do it twice. We're going to do it first for the first eigenvalue. So we take eigenvalue, the first one, eigenvalue 1 equal to 2. And then we are thinking of this here, 2i. This is lambda's filled in to be 2, x is equal to 0. That is exactly the same as saying ax equals 2x. Okay, we've identified this eigenvalue of 2. So we make this computation here with the lambda equal to 2, and we get and we want to solve this system right here and find which vectors x make this true. So what does that look like? 2I minus a looks like this, 2 minus 6, 1 minus 3, and then we want to know for what values of x does that equal to 0. I'm just going to roll back here and show you what I'm doing in case it's not clear, and that is I am substituting in 2 right here. I don't have to do a lot of calculations. It's sitting already right there from having found the eigenvalues. That is 2 minus 6, 1 minus 3. Okay, so there it is. Okay, I do the row operations to see what happens here. And first I'm going to swap the first two, the row 1 and row 2. And then I am going to take row 2 and minus 2 times row 1. Okay, and that leads me to the fact that V1, the eigenvectors associated with lambda 1 are these ones here. Okay, so that is, let me just circle this, that is the eigenvalue, one of the two eigenvalues, and that is its associated eigenvector. I'm going to do exactly the same thing now for lambda equals to 3. So I'm going to take the second eigenvalue, that is 3, and now I'm solving the equation ax equals 3x, and that is equivalent to solving the system 3I minus a multiplied by x equals to 0. So now I'm going and taking a look at the same thing here, and I'm putting in 3 here and here. So I found those two values. Okay, so I go ahead and do that. I get this system here. 3 minus 6, 1 minus 2, 0, 0. And I go through with the row operations, and I get to this reduced row echelon form here. And then that allows me to identify that the eigenvalues, the eigenvectors associated with the second eigenvalue are these guys here. Okay, so let me just circle those in a different color. So for this eigenvalue, we have these associated eigenvectors. Okay. Next, we have the idea of an eigenspace. Okay, we just saw that the roots of the characteristic polynomial are eigenvalues of A, and for each eigenvalue we have eigenvectors, and those eigenvectors are the solution space of this linear system of linear equations here, and they contain more than just the zero vector. Let us just look back. For example, here on lambda 2 is 3 and v2 is equal to this. Clearly, if t is 0, it contains this zero vector, but t can be any number. So t here is that parameter that we often have been using. It's a real number. So there's many other values. Okay, so let us then observe that the eigenspace is the space spanned by the eigenvector. Okay, so let's just write that out for one example here. So this is the above example, the same matrix. So in our example, we had A is 0, 6, minus 1, and 5. We found one of the eigenvalues to be 2, and we found that the corresponding eigenvector was this. Okay, and then the solution space is all the vectors t, 3, 1, t in R. Okay, so that's what this is telling us here, this definition, the eigenspace. The solution spaces are those vectors x such that lambda I minus a equals x is equal to 0. And that's the eigenspace of a corresponding to the eigenvalue, whichever one we chose. In this case, we chose lambda 1 is equal to 2. Okay, you notice it's in space. It's not just a subset. And so in this case, we have a 2 by 2 matrix. We are in R2. This example, we are in R2, and that's this example. Oops. And T3, 1 is a line through the origin. So you remember, what are the subspaces of R2? The subspaces of R2 are the possibility of just the 0 vector, all of R2, or any line through the origin. Okay, so if we have some non-zero vector in the eigenspace of lambda, then that is an eigenvector corresponding to lambda. Okay, so let's just check this out. We've gone ahead and done all this work. Let's just check that it actually works. So let us just check this exact example, and maybe that'll also shed some light on exactly what we're doing here. So we've got this matrix A like that, and we've done these calculations. We've found the eigenvalues and the corresponding eigenvectors. So let us take a look again at this one here, and we found this. Okay, what this is telling us, this is what we expect, given how we started this, what we're trying to find. And so let us just check. We expect that A multiplied by V1 will equal 2 times V1. That is the expected situation, because that is what these things are. Right? That is the definition there of what is an eigenvalue and what is an eigenvector, and we found them. So let's see if it works. So how we're going to check that is we're going to take A, and we are going to multiply it by V1. V1 is 3t and t, and we expect, and we're going to check, is that equal to 2 times 3t and t. And so I've just filled in all of the things we found. I filled in A, I filled in V1, I filled in lambda 1 is equal to 2. So I'm going to, now on the left-hand side, I'm going to do this matrix multiplication, matrix times vector multiplication. And so I go ahead and do that, and I get this here, 6t, and then I get minus 3t plus 5t, which gives me 2t, and then does that equal, and I get here 6t and 2t. Yes, it does. Okay. All right, so we could then phrase this in this manner: find and graph the eigenspaces of A. Okay, so we've already done all the calculations we need. There's no new calculations here. I will simply write below here what we need to know to do this. We need to know the eigenvalues, and we need to know the corresponding eigenvectors. And then we can simply draw that onto the graph. So let's do, sorry about that. Here, I got this thing keep coming up on here. Let's do this one here first. We've got, we can just pick a value of t. Let's pick t is equal to 1. that will mean we can plot a point right here, 3, 1, right here, like that. And then we can draw a line through that. I'm going to go here. I'm thinking of t as -1, and I'm going to go here -1, -3, just to get a second point to attempt to draw a line through here. This is a straight line, folks, coming through here like this. Okay. So that is that line is, this is the eigenspace corresponding to lambda 1 is equal to 2. Then I'm going to do exactly the same thing with the other eigenvalue. And so now I'm looking at this one here, and I'm thinking, okay, let me just take t is equal to 1 so I can get a point. So that's going to be 2, 1. So it's going to be right here. And I'm just going to get myself another point. And I know that 0, 0 is also a point on this line, but let me just get another one down here so I have stand a better chance of drawing a straight line. So that's going to be like right here. And so I draw that coming, that straight line right there, coming through that point, and that point, and being a straight line. Okay, so that is the eigenspace corresponding to lambda 2 is equal to 3. Okay, so what we've seen: eigenvalue, eigenvector, eigenspace. Now we're going to just take a bit of a diversion. We're going to look at the eigenvalues. It's not really a diversion, but we're going to consider what happens when we have our special matrices. So we've saw different types of special matrices, and we're going to see that for some of them, it's very easy to get the eigenvalues. So if we have a triangular matrix, the eigenvalues are the entries on the main diagonal. So that is a very nice feature, very fast to get at those. So let's just see an example of that in action. Let me just get a lower triangular matrix. It doesn't matter if it's upper or lower triangular, it applies to both. But let's get a lower triangular matrix here. There's a lower triangular matrix, and I claim that the eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 2, lambda 3 is equal to 3. Okay, so that is true, but let us just go through the procedure this one time. Never again am I going to probably go through the procedure when I have a triangular matrix, because I can simply write out what the eigenvalues are. But this time, let me do that. I can take lambda I minus a. That will be equal to this, lambda minus 1, 0, 0, and then 1, lambda minus 2, 0, and then 3, 4, and lambda minus 3 there. Okay, and then I can take the determinant of that, determinant of lambda I minus a, and well, I mean, you see what happens when I take the determinant. I do the cofactor expansion here, and I get lambda minus 1, and then the other ones are 0, and then I take the determinant of this 2 by 2 matrix right here, which is lambda minus 2 times lambda minus 3. And there we can see when I set that equal to 0, I do get those eigenvalues that I claimed. Okay, so that's that in action. The triangular matrices are also very nice. Okay, here's another theorem. If we have an eigenvalue of a square matrix A and its corresponding eigenvector, and we have a number k, positive integer, then lambda to the k is an eigenvalue of ak, and x is the corresponding eigenvector. Okay. All right. So I want to do an example here. Let's just Let's just do an example. Okay, I'm doing this example here on the fly, so hopefully I don't make any mistakes. Let's take a 2 by 2 matrix like that. Why don't we take one we've already done, like this one here, 0, 6, minus 1, 5. 0, 6, minus 1, 5. Okay, we already know that lambda 1 is 2 and lambda 2 is 3. Okay, so now the claim is that if I take, say, for example, a squared, that without any further work, I could say that lambda 1 for this new matrix, let me just call that prime, that would be then 2 squared, which would be 4, and lambda 2 prime would be 3 squared, which would be 9. Okay, so that is the claim here, and that the x is unchanged. The eigenvalues the eigenvectors are unchanged. So let's just quickly see if that works in this case. This is not a proof, of course. This is just an example showing you what the theorem is telling you. So let us figure out what is a squared. Okay, that is going to be equal to minus 6 here, 0, oh boy, numbers are getting big, 30, minus 5 here, and 6, minus 6 plus 5, that would be minus 6 plus 5 minus 1. Hang on, I'm going to check this again. That's minus 6, 0, 30, minus 5, minus 6. Uh-oh. Something looks wrong here. Minus 6, it's actually minus 6, not plus 5. It is minus 6 plus 25. Oh no, minus, minus 6 plus 25, that is 19. Minus 6, 25, minus 6, 19. Okay, all right. Lesson to self, don't try examples on fly. But let us see if I can proceed on here. We will attempt to calculate the eigenvalues of this, and I'm hoping that they will turn out to be this. They should be. Okay, so let us do that. We have to find the determinant of lambda I minus a. That's going to be the determinant of lambda I minus a. That's going to be the matrix here. That is going to be 6 lambda plus 6 minus 30, 5 lambda minus 19. And then we get here, lambda plus 6, lambda minus 19. And then we have minus 150, minus 150, and I take the negative of that, plus 150. Let's see, lambda squared. This is brave, man. I'm forging ahead with this example. Minus 13 lambda, and then that's going to be 150 minus, okay, I got to go 19 times 6, that is 54. Carry the 5, that's 114. That's minus 114, so then it's 150 minus 114. Oh man, the chances of this working out are low. 6, 3, 36. Oh my goodness, 9 times 4 is 36. Oh, thank goodness. Okay, right? Let us now factor this, folks. I've got my keyboard happening here. I'm going to factor this. I get lambda minus 4 and lambda minus 9. And then I get these two guys right here. Whew. Okay, so it did work in this case. So clearly, I mean, were you to have this information, clearly finding these two numbers here is much faster if you want to know what the eigenvalues of a squared or a cubed or a to the 4. But we did do it, and we saw that this example of how that works. Okay, what happens if one of the eigenvalues of a is 0? Okay, let's think about what that would mean. This would mean ax equals lambda x would be 0 because lambda would be 0. And that would mean that ax would be equal to 0 for non-zero x. That implies that the determinant of a is equal to 0. Okay, that comes from our unifying theorem. And so that is how this guy gets added here onto the end, okay, right here. This thing just keeps getting longer and longer. We're now up to J. We started out with, A, B, and C, I think was our first one, and now most lectures we've been adding to this thing. So we want to recognize that all of these statements are equivalent, and we just saw, so this one here that's been added here, what is the reasoning for that? We just saw that det A equals 0 if lambda equals 0 is an eigenvalue. Okay, so this is just the statement, those two statements I've boxed is just the negation of that. So therefore, that A is not equal to 0 implies lambda equals 0 is not an eigenvalue. And our unifying theorem grows in length by 1. Okay, next point. We can have complex eigenvalues and eigenvectors. So please make sure that you've watched the complex variables lecture, which was on Appendix B of the Busby textbook, because that goes over the necessary arithmetic and such that we need with the complex numbers to be able to handle the idea of a complex eigenvalue. Okay, so let us go ahead and find the characteristic polynomial of this matrix here. So we do what we're going to do every time. We take the determinant of a lambda I minus a, and that is the determinant of, and this is when I'm going to stop putting in all of the steps every time, because you can do this in your head after you've done it a few times. Maybe stop the video right now and compute the eigenvalues of this matrix yourself. See if you agree with me. Okay, so now we're going to have to take the determinant. I'm going to do the cofactor expansion along the second row here because of those two zeros. So that will lead me to this thing here. This is here negative. So that's positive there, lambda minus 2. Yeah, negative, positive, yep. Then I'm going to go here. Lambda minus 1, 5, lambda plus 3. And that's going to be lambda minus 2. I could do this in the next step. Lambda minus 1, lambda plus 3, minus negative 5. Okay, that's going to be lambda minus 2, lambda squared plus 2 lambda minus 3 plus 5. And that's lambda minus 2. And that's going to be lambda squared plus 2 lambda plus 2. Okay, so we know one of the eigenvalues is going to be 2, and then we're going to get 2 eigenvalues from this here. And so I'm going to look at when does lambda squared plus 2 lambda plus 2 equal to 0. And that occurs when lambda is equal to minus 2 plus or minus the square root of 4 minus 8 all over 2. And that is lambda equals minus 1 plus or minus I. Okay, so we have here, well, a few things. We got asked to state the characteristic polynomial, so why don't we just do that? Characteristic polynomial, p of lambda, is equal to lambda minus 2 lambda squared plus 2 lambda plus 2. And the eigenvalues, minus 1 plus I and minus 1 minus I. Okay, so we can have complex eigenvalues. Notice these complex ones always come in pairs, with one being the conjugate of the other. Okay, so a bit more stuff here. If we've got a n by n matrix with real entries, then the characteristic polynomial has degree n, and the leading coefficient could be is 1. And we have all those. We have these numbers here. That's fine. Okay, so the fundamental theorem of algebra, tells us that we can factor the characteristic polynomial p of alpha into n linear factors, and these numbers here are the roots of the characteristic polynomial, and each can be real or complex. So every n by n matrix has exactly n eigenvalues, but it may have fewer than n distinct eigenvalues. So we have this idea of a multiplicity. This is just the same as finding roots of polynomials that you may have already seen before. Okay, so our theorem is telling us here our characteristic polynomial will, when factored, look like this. We will have some number of distinct eigenvalues, and each distinct eigenvalue can have a multiplicity of 1 or more. And when you add up all of those values, m1 to mk, it has to be equal to n. That's by the fundamental theorem of algebra. And these exponents here, m1, m2, etc., those are, well, let's just talk about m1. It's easier to state it. If we just look at m1, m1 is the algebraic multiplicity of eigenvalue lambda 1. Okay, so let's just write out an example here. We can have a characteristic polynomial that looked like this. There. So this is a degree 5 polynomial. We have two distinct eigenvalues. So here we have two distinct eigenvalues. Lambda 1 is equal to 1 with multiplicity of 2, and lambda 2 is equal to 2 with multiplicity of 3. And you will see that 2 plus 3 is equal to 5, which is equal to the degree of p of lambda, and that this characteristic polynomial came from a 5 by 5 matrix. Okay, I want to take a couple more examples to conclude this whole situation here. Okay, so we're going to take a look at a larger matrix. We're going to find the characteristic polynomial and the eigenvalues and see what the algebraic multiplicities of those eigenvalues are. So we'll do that this way. Determinant of lambda I minus b, and that is going to be this guy here, lambda minus 3, 6 minus 2, 0, 0 lambda minus 3 0 0 0 5 lambda minus 1 lambda plus plus 1 0 2 minus 5 lambda plus 1, like that. So we have to take the determinant of this, made less daunting by the fact that there's lots of zeros. So we're going to do the cofactor expansion along the first column. So I would get this here then, lambda minus 3 times the determinant of the resulting minor, that is this guy here. Okay, and then I'll do the cofactor expansion along the first row this time, and that's going to get me this here. And what's the resulting minor? And then I can proceed to use the 2 by 2 case to finish this process up, and that will be lambda minus 1, lambda plus 1, and plus 5. That gets me this here. Lambda minus 3 squared, lambda squared plus 4, and then I factor, and I get here lambda minus 2i, lambda plus 2i. So I have the eigenvalues lambda 1 equals 3 with multiplicity 2, and I have lambda 2 is equal to 2i, and lambda 3 is equal to minus 2i. There they are. Okay, a couple of other features. We're just going to express the characteristic polynomial of your general 2 by 2 matrix using the trace and the determinant. So let's just note what the trace and determinant of that matrix is. That is, the trace is the sum of the diagonal entries. So the trace of A is A plus D, and the determinant of A is AD minus BC. So now I'm going to compute the determinant of lambda I minus A, and that is going to be this thing here, lambda minus A minus the determinant of this here, minus C, lambda minus D, and that's going to look like this, lambda minus A times lambda minus D minus BC, and that is equal to lambda squared minus A lambda minus D lambda plus AD minus BC. That is lambda squared minus A plus D lambda plus AD minus BC. And so our trace is sitting right there, and our determinant is sitting right there. So I can see that for the 2 by 2 matrix, the characteristic polynomial, I can write it this way: the trace of A plus the determinant of A. I could, if I want, I could go directly this way with these two calculations right here. Okay, so we now have the sort of general case sitting there. So what are the possibilities for the eigenvalues of A above? Well, there's the three possibilities. It's a quadratic, and we find the eigenvalues by setting this thing equal to A, and the possibilities are determined by the values of the discriminant here, that which is b squared minus 4ac in the quadratic equation. So what are the possibilities? Let's figure out what b squared minus 4ac is. We can see here a is 1, b is minus the trace of a, and C is the determinant of A. Okay, so this guy here in the quadratic formula, is this the trace of A squared minus 4 times the determinant of A. Okay, so what can happen if the discriminant here, so that is this, if the trace of A squared minus 4 times the determinant of A is greater than 0, that leads to us having two real eigenvalues. If the trace of A squared minus 4 times the determinant of A is equal to 0, we get one distinct real eigenvalue with multiplicity 2. And then if the trace of A squared minus 4 times the determinant of A is is less than 0, that's the third possibility, we get two complex eigenvalues. Eigenvalues 1, the conjugate of the other. And those are the three possibilities. For any of you taking, maybe you wouldn't be taking that yet, but many of you will take subsequent to this course, the first course in differential equations, Math 260. I believe this course to be a prerequisite. And you'll see the same thing. Differential equations have a characteristic equation, and then the roots of that characteristic equation fall into these three categories, and then that tells you about the behavior of the differential equation. It's quite analogous to this situation here. Okay. All right, a couple of other points. What happens if we have a symmetric matrix? So A is symmetric, and we're looking at the 2 by 2 case here. We have a symmetric matrix, 2 by 2, and we want to know, can we say something about the eigenvalues? So let us just set up the basic case, the general case of the 2 by 2 symmetric matrix. That looks like this. Okay, and then we'll compute the eigenvalues of that. That is going to be this. That is going to be okay. That is the characteristic polynomial sitting right there. So let us just rearrange that a little bit. That's going to look like this. Okay, now let's take a look at the discriminant in the quadratic equation in this case. This is b squared minus 4ac from the quadratic equation. In this case, that will be, it's a little bit confusing because we got a's and b's meaning different things, but that will be, in this case, we've got b squared will be this, a plus d, well, it's negative of it, but it's squared, like that, minus 4ac, which will be this. Okay, and well, what you can see right away is that this is always greater than 0 if the matrix itself is not 0. Okay, and that means that symmetric matrices always have real eigenvalues. Okay, just going to end with an example. Highly recommend that you just stop the video right now. Just do this calculation. In fact, maybe because I've just done this so many times, I think what I'll do is I'll just say what the answer is here. Leave this for you to calculate. This is just two cases, and you want to be able to just find the eigenvalues. So I found the eigenvalues for A. So in the eigenvalues of A, I got lambda 1 is equal to 3 and lambda 2 is equal to minus 2. The eigenvalues of B, I don't actually have it written down here, so I may have to write this out. Hang on a sec. I got the characteristic polynomial, so let's look at B. I got a characteristic polynomial that looked like this. Lambda squared minus 4 lambda plus 13 is equal to 0. And then if you use the quadratic equation, I found that lambda 1 is equal to 2 plus 3i, and lambda 2 is equal to 2 minus 3i. Okay, so just an example in the 2 by 2 case. You got to be able to find eigenvalues and then the corresponding eigenvectors quickly and efficiently. Okay, that's it for now. Yeah, I'll be back with the next section shortly. Bye.